Going to be working on example problem number 6 from your homework packet. This is just so that you have everything in front of you and you don't have to copy down this problem. So in the problem, we're told that there's a convex mirror that is reflecting light from an object that is 66 centimeters away from the vertex in front of the mirror. And we're told that the focal length of the convex mirror is specifically negative 46 centimeters. We're asked to determine the image distance, the magnification, to classify the image as being either real or virtual, to compare the size of the image to the size of the object, and to determine whether the image is upright or inverted, and then draw a ray diagram that corresponds to this. So we're going to do this kind of all together now to try to get this in one foul swoop. So when we're determining the image distance, right? We have a couple of different options. We can use either the lens-maker equation, the 1 over f equals 1 over di plus 1 over dou, or we can use the magnification equation, that is image height over object height, high over ho, is equal to negative di over dou. Quite honestly, we don't have any information about the image height, so I am going to cheat and kind of just say, I'm not, nor are we really asked about it that much, so I'm getting rid of this for a second here, okay? And I don't have enough information to use the magnification equation yet, and I'm going to probably use it for the magnification. So I'm going to go ahead and use my lens-maker equation. So I'm going to have 1 over f equals 1 over di plus 1 over do. Now, again, making a list is a great thing. So we've got my focal length is negative 46 centimeters. My di is what I'm looking for, and my do is 66 centimeters. Okay. Hold up. If you look at this, aren't we adding 1 over length plus 1 over length is equal to 1 over another length? So if we leave as long as our units match, we're not multiplying by any constant, we're not trying to convert it into anything, we can finally leave the units what they are so long as they all match. We're all in centimeters, I'm leaving it in centimeters. I don't feel like playing around with conversions, and hopefully you don't either. So my 1 over the focal length equals 1 over di plus 1 over do. Well, I know the focal length and I know do, so I can say 1 over the focal length minus 1 over do is equal to 1 over di. Okay. But I don't want 1 over di. What I want is di. So di would equal 1 over the focal length minus 1 over dou, that raised to the negative 1 power, which would be 1 over negative 46 centimeters plus minus, this is a minus sign, so minus 1 over 66 centimeters, raise that to the negative 1. We're going to need to punchy in our calculator, so I am grabbing my handy dandy calculator, and I am taking 1 over negative 46 not divided by, but minus 1 divided by positive 66, and raising that to the negative, that quantity to the negative 1. And I'm going to evaluate it because I always want full numbers whenever possible. And so my di turns out to be, we get negative 759 over 28, which is equal to negative 27.10714, on and on, or my final answer, negative 27.2 centimeters. Okay, done with part A. Now that we know that, I'm going to jump in and do part B, determine the magnification. When we determine the magnification, we're going to just use that magnification is equal to, and we've already picked it out, negative di over do. So My magnification is going to be negative 759 over 28. And why am I using the fraction? Because the fraction is the whole number. It has every digit in it. And I'm feeling like doing that. And then divide that whole thing by positive 66. So I'm going to take negative of my original answer and divide it by 66. And that leads me to 23 over 56. And when I evaluate that, I get that the magnification is 0.41071 and the magnification to three significant figures would be 0.411. Now, using only this information and what this information means and what it's telling us, I'm going to answer the next three problems before I start in on my actual ray diagram. Okay. So I want to have, so we can see the answers. Sorry, getting those in there. Okay. So when I'm doing this, I can say that from my answer, from the fact that DI is a negative number, a negative DI tells us that the image is virtual. Okay, since my image distance is negative, that tells me it's virtual. All right, is the image smaller, larger, or the same size? Well, for that, I'm going to go to the magnification. Okay, if the magnification is greater than 1, it's going to be bigger. If the magnification is less than 1, smaller. And guess what? If the magnification is equal to 1. If you guess same size, you are right. Good job. Okay. So let's look at our magnification. Our magnification, and notice I'm saying it's the absolute value. The sign of the magnification simply tells you upright or inverted, but the value, the magnitude of the magnification tells you bigger, smaller, or the same size. So looking at this, we've got a magnification less than 1.4, so it's going to be smaller. And by knowing that it's virtual and that the magnification is positive, both of those point to it being erect and upright. Okay. And for our proof. Now, quite honestly, C, D, and E, you could wait. You could do these after the ray diagram, if that is easier for you. But you can do them before. All good. Okay. So for the ray diagram, I'm going to come down here and I have a primary axis that doesn't have my optical device on it yet. And that's because I need to sketch my optical device. We were told it's a convex mirror. So the first things first, I have to sketch a convex mirror. Convex mirror is basically part of a circle bowing out. So I'm just going to throw that down there. Okay. We were told that the focal length is a negative 46, so this is 46 centimeters behind. And the focal length is also 46 centimeters, so F is 46 centimeters in front of. And then C is twice 46, which would be 92 centimeters. All right. So I am going to grab a pen and my handy dandy ruler to make this happen. And I want to draw an object, which is just an upright arrow, somewhere in between, because it's at 66 centimeters, which is in between 92 and 46. Exactly where, don't care that much. It just needs to be in the right general area, which in this case means it's in between. Okay. Then our first incident ray goes in horizontally parallel to the primary axis. It is a diverging mirror, so our first reflected ray is going to bounce off, making an angle with the virtual um, uh, focal point. And then I aim the second incident ray. Oh, don't forget my little arrow going away. I aim my second incident ray using the tip, the convex mirror, and the virtual focal point, stopping when I get to the convex mirror because the light's going to stop going in there and now it's going to start coming out. If it goes in diagonally, it's coming out parallel. That didn't go real well. Okay. And I'm like, yeah, those two lines never going to meet. So I want to extend this backwards. And this is my image. Okay. So using this, I can say that my image is smaller, it's upright, and it's virtual because it's where the lines come together by extension rather than actually coming together. All right, thanks.